Mixed parametric and self-oscillations with the delayed damping. Alishir Alifov, Mechanical Engineering Research Institute of Russian Academy of Sciences, Moscow. Models, equations of motion. Frictional self-oscillations are described very well by the model shown in Figure 1. Figure 1. Body 1 with, with mass m lies on the belt, which is driven by an engine having a torque characteristic, where is the speed of rotation of the rotor. The friction force Tu arising between the body 1 and the tape depends on the relative speed. U is equal V minus x dot, V is equal R0 phi dot. Under certain conditions, it can uh, cause self-oscillations of body 1. The damping forces depend on the delay, i.e. x dot eta is equal x dot t minus eta. Eta is the delay. We can see the system model on the figure 1. Nonlinear differential equations describing the system's motion have the form mx dot plus kx dot sub eta plus c sub 0x is equal to t of u minus f of x minus bx cosine vt. I phi 2 dot is equal m phi dot minus r sub 0 t of u. We represent the nonlinear part of the elastic force in the form f of x is equal sum gamma sub s x super s is equal to 3, 4, and so on, and the friction characteristics in the form t of u is equal r sine function u plus f of x dot. F of x dot is equal to sum, and coefficients have the following form. We can see following form of coefficients. Here, gamma sub s is equal constant, r are the normal reaction force, alpha sub r is equal constant, sine function u is equal 1 at u is greater than 0, and sine function u is equal minus 1 at u is less than 0. At relative rest, u is equal 0, minus r is less than or equal t of 0 is less than or equal r takes place. A special case of characteristic 2, which is widely used in the practice, is t of u is equal r sine function u minus alpha sub 1 u plus alpha sub 3 u super 3, which was also observed in the conditions of a space experiment. Using the direct linearization method, we replace the nonlinear functions f of x dot and f of x with linear functions f sub asterisk of x dot is equal b sub f plus k sub f x dot. F sub asterisk of x is equal b sub f plus k sub f x, where b, k are the linearization coefficients which are defined by the expressions. Equation 1 is connection with 3. Take the form. We can see the form, the next form of the equations 1 with 3, where b and c have the following form. B and C have following form. Solving equations. To solve 5, we use the method of replacing variables with averaging and the procedure for oscillatory systems with non-ideal energy sources, described in uh, and respectively. In this method, using the solution form, x is equal a cosine psi, x dot is equal to minus v sine psi, psi is equal pt plus xi. For the linearized equation, the standard forms of the equation are derived, which allow us to determine the non-stationary and stationary values of v and xi. Taking into account the Mach and v is equal ap, p is equal v under 2, x dot sub eta is equal minus v sine psi minus p eta, we obtain from 4 the following equations for determining the amplitude a, phase xi, and velocity u. A. U is greater than or equal AP. We can see the following equation. And B, U is less AP. We can see following equation, where as a result of averaging, V is equal R sub arrow phi dot is replaced by U is equal R sub 0 omega in the expressions alpha sub 0 and alpha sub 5 included in 3. A is equal P k cosine P eta minus RK sub P is equal M omega super 2 sub 0 minus P super 2 plus K sub F omega super 2 sub 0 is equal C sub 0 and M psi sub asterisk is equal to pi is minus arcsine U over AP. The equations for stationary motions are obtained in the case of U is greater than or equal AP from 6 for A dot is equal 0 and C dot is equal 0 and U dot is equal 0, which provide the following relations for the determining the amplitude and phase. A super 2 plus E super 2 is equal B super 2 over 4. Tangent to C is equal minus A over E. The amplitude in the case of U is less than AP is determined approximately by the formula AP is equal U. The equation for determining the stationary values of the velocity U is obtained from the condition U dot is equal and has the next form. We can see the form of the equation. Stability of stationary oscillations. It is necessary to check the stability of stationary movements. To this end, we compose the equations in variations for 6 using the Roth-Hurwitz criteria. Further, we have the following stability conditions. D sub 1 is greater 0, 3 greater 1, d1, d2 minus d3 greater 0, where d1 is equal minus the next expression, d sub 2 is equal this expression, and d sub 3 is equal this expression. In the case of u greater than or equal ap, velocities take place the coefficients. We can see these coefficients b sub 1 1, b sub 1 2, and so on and so on, where q is equal the next expression. The expressions are not shown here due to their large size. Solid curve 1 corresponds to no delay eta is equal 0. Dashed curve 2 minus p8 is equal pi over 2. Dashed curve 3 minus p8 is equal to pi. The corresponding self-oscillation amplitudes are shown by a sub 0, a sub 1, and a sub 2. Amplitudes above the a sub 0, a sub 1, and a sub 2 levels are stable. Bold sections of the curves and low fat section of curves are unstable. Oscillation with amplitudes are stable if the values of the steepness q is equal. Derivative m with respect to u of the energy source characteristics are within the shaded sectors. Conclusion. These results of calculations show the effect of the delay in damping of the dynamics of the system. It shifts the amplitude frequency curve up down. Hence, it follows that with the remaining unchanged parameters of the system, if there is no resonance curve, i.e. oscillations, in the absence of a delay in damping, then in its presence it can appear. In contrast, the delay in elasticity shifts the resonance zone both to the right-left and up-down. Thank you for attention.